Okay. 5 after, let's get going. I will let you join.
Hey.
So one thing I wanted to mention, since I started to look at least just even begin to glance at the segmentation thing, it made me realize something that is sort of, I think I gave somewhat of a wrong answer last time when Siva asked me about, the ResNet I was using and the size of the inputs to it and stuff that I wanted to clarify. It's not wrong as much as a couple of things there that I wanted to clarify. What I'm talking about is, Siva had pointed out that, hey, you're using 3-channel input to the 3D. And as I said then correctly, you could use 1 channel since most of the images are just kind of grayscale, or you can use 3 channels. The thing I figured out very quickly when I started actually applying it is for anything more than the 64 by 64 by 64 voxels, if I use 3 channels, I run out of memory immediately. So I had to go back to making the ResNet model a 1 channel by 3D. And that's an important thing I wanted to point out, that if you try to use a 3-channel, but with, any bigger size of images, then you immediately run out of memory for anything bigger than 64 by 64 by 64 voxel size. That's, sorry, any comment?
I see. Yeah, I was, the one notebook I had originally, it was like either 64 by 64 by 64, but I did get 128 by 128 by 128 to run, but yeah, it was single channel.
I did too, but it has to be single. If you try 3, then Kaggle runs out of memory.
Okay. I remember I tried, so Monai has this thing where it lets me try like 64 by 64 by 64 by 4, right? So use all 4. I need to see how big of a size I could get into that. Like I was initially, I want to, I'll check and later I'll let you, if I was able to do,
so
like what 128 cube into 4 or not. I'm not sure. I'll check that.
Yeah. So at least when I tried it on Kaggle, for anything bigger than 64, it would, no matter how much I reduce the batch size, I was down to like 8 or 4, and it still wouldn't run. And I was like, well, I mean, using 2 doesn't make a whole lot of sense. So I figured out that it was because I was using the 3 channels. So that's point number 1. Point number 2, which is more related to something that I was telling Steve with respect to the segmentation that notebook that he shared, and after reflecting on it, and also because of this particular issue I faced, something I realized that I wanted to highlight. Which is also related to the point that Siva brought up of, hey, you're using 3 by blah, blah, blah. The thing I wanted to point out is that while I commented on to Steve that it may be helpful to, for the segmentation to kind of chop on the X and the Y and the depth, like meaning focus on just the portion of the image that has the tumor. One thing I realized why, and this may be among the reasons that the person is actually just using, the slice that has the most tumor pixels in it and using the entire slice, is because the thing, if after thinking through it, you realize is that in order to batch the images successfully, you need all the images to be of the same size. Otherwise, you can't batch them, even if they are 3D, right? So each 3D input can't be of a different size. In order to batch, just like every 2D image has to be of the same size, that is, every single input you provide to a batch can't be of different sizes. It's the requirement of batches that they be of the same size. So if that's the case, then I just realized that in any segmentation output that we provide, we can't segment to the exact size of the tumor because that will vary. It will have to be some standardized size. It may be the size of the smallest tumor or whatever we choose, or slices of a particular depth, but it has to be all of the same dimensions in order for it to be batched successfully.
Yeah, that
Does that
paper I
make
shared
sense?
with you. Yeah, the paper I shared with you, like the one that they've got like a pretty good result on MGMT classification or whatever. That's what they do. So they run like a UNet to do the segmentation, which gives them like a small, what's the word, cuboid within the brain. And then they split that up into 32 by 32 by 32 even smaller cubes, and like then use that in the classifying part. So yeah, like they use the segmentation to identify which part of the brain, and then they chop that up into smaller bits.
But all of the same size.
Yes. Yep.
Yeah, that same size thing was, it should have been obvious, but sometimes the obvious doesn't hit you unless you get close to it and you go, oh, wait, I can't really, or, it has to be. So that led me to this thought, Steve, that it seems, and maybe you can update us on this, it would appear that in order to do rely on the classification, you would have to decide if you're using this segment first and then classify approach, that you'd have to kind of first pick the kind of segmentation model approach that you're using, and then the classification kind of depends on the results or output of what your segmentation model choice is, right?
Yeah, that's sort of what I'm going with. Yeah, and like as I say, like that's sort of the approach they took in that paper that I'd shared before. But what I was showing you last week was, so like I'm running a segmentation model. The classification bit that I had, it was based on the one that's like the sort of, it was like the leading score thing. It was like the efficient 3D paper, and like what they were doing, they were taking just like the images or whatever and taking the middle slice. And so yeah, like last week my approach was to, rather than just taking the middle slice out of the DICOM set, to use a segmentation model to do like a 2D segmentation, and then find the slice with the most pixels on it and use that as like the middle slice to use, as opposed to just the numerical middle slice. And then what I was going to do was, like it does tell me whereabouts the tumor is, and so like I can like cut down from like a 3D cube of the whole brain down to a small cube, and then I was going to slice that up more into like regular sized bits.
Yeah, and the thing I was thinking of, and since I think you and Naval have done most stuff, I think, on segmenting stuff, is there any way that the segmenting can work on, there's no reason why the segmenting approach that you have should not be able to work on the voxels and identify the voxel slice that has the most pixels, for example, correct?
Yeah, that's actually what I've done this week. So like completely remade all of my input data. So yeah, like the segmentation model that I had like previously, it was using like the 2020 BRATS data. But like like it was using the Nifty files. So like I've completely redone it now to make like 3-dimensional NumPy voxel arrays, and then retrained the whole segmenter on that. Yeah, like it's pretty good now. It's like it's very, very accurate, seems to be in predicting them. And then I've like
Cool.
completely remade all of the DICOM data in exactly the same way. So it's exactly the same size as the segmenter. But I haven't got as far as like actually running the classification on it yet. But yeah, so like now I've sort of completely remade all the data, and it's both my segmentation data set and my standard competition data set are made in the same way, and they're both the same shape. So hopefully the segmentation now should tell me the area where the tumor is, and like then because of the fact that they're all the same shape, then it should be the right area for all of the different 4 MRI types.
So what segmentation model are you using? Is it like something public model, or is it something that you build on the fly? Or
no, like it was like the one I showed last week. Hang on a sec. I can share my screen and show.
Yeah.
It's just the if I can find it. I've got so many notebooks now, it's hard to keep track of them all. Yeah, so yeah, it's just like some Keras segmentation thing. So yeah, like I do like a lot of stuff. So here, these images here, yeah, so I've taken like what were the Nifty images and resized them and cropped them. So like this is like the axial view here. Did I go too big? Yes, like this is the axial view. So like that's the flare of the T1, and this is the segmentation thing. So you can see like here in the flare, it's pretty identical to that. So all of these images now, I've taken them from the Nifty data and made it's 240 by 240 by 240 cubes from the brain, and like the brain now like fills the whole area at its largest bit, and then like the UNet is just yeah, like this was just from some notebook that was out there, so it like takes in 240 as well. So I just retrained that, so you can see here unlike the validation accuracy, like on the validation set now is up really high. So in the validation set, like in the training, like they're nearly, it looks like they're nearly almost precise. And you can see here, like, so this is like running on like one of the, I think it's actually a training image. But yeah, so like the red is my prediction, the blue is the actual, and the two of them match up. And yeah, like here because of the fact they're purple, this is all pretty much matching up. So holding that, and then as I say, like I've sort of run the same processing code or similar processing code on the competition DICOM data. So hopefully it should tell me which of the slices has the most the most tumor on it or whatever, and then I should be able to like just hopefully like take this area here and then concentrate on that with the classifier. But I haven't got that far yet because
yeah, no, but that's I think your approach is perfectly the correct one. The only comment I would add is one of the notebooks that I think Mehul shared points to something that would be relevant, I think, in your approach. And that is the fact that the task one, that is the segmentation data for BRATS 2021, has, and that particular notebook that Mehul pointed to, compares the patients, for lack of a better word, I'll keep it as patients, because in one case, it's in the task 2, which is the classification task, it's referred to, I think, as BRAT's whatever ID. And in the case of task 1, which is the segmentation task, I don't know what they call it, but this guy in the notebook compares and I'm going to call it patient just to keep it simple and abstract out the difference that the two tasks refer to them differently. But so he points out which patients are common in both and which are unique in both. And the reason, and by both, I mean in both tasks, as well as he goes down to comparing it in the training and the test data sets. The reason why I think, Steve, that with your approach, that data that he points out becomes important, as I was thinking through it, and correct me or comment on it if I have this wrong, but there are many more instances of images or patient images that are available in task 1 than in task 2. And there are some in task 2 training itself, which are not there in task 1, like 8 images or something like that. So if that's the case, I just wanted to run, would you approach it this way, that you would train the segmentation model on all of the available images in task 1, just to get a better segmentation model. And then you would apply it to all of the training images which are common between task 1 and task 2, and whether in train or in the in the training set. And then you would use that model and to treat even the 8 task 2 images which are not available in task 1, therefore they do not have the corresponding mass. Would you predict the mass in those even in training when you're doing classification? Do you follow what I'm getting at?
Sort of, but I'm not actually using the task 1 images at all at the minute. At the minute, my segmentation model is just trained on last year's 2020 BRATS data. So it is just purely like a segmenter or whatever. So it doesn't use any of like task 1 images yet.
Oh, I see. So
it's
you're just using
like
the model as is. I see.
Yeah.
To predict
so
on
I'm
all
not
task
using any of
2 images?
Yes.
Okay. I see.
Yeah, so like all I've done is create like a segmentation model to find brain tumors, but I haven't used any of the task 1 data, so I haven't used any of this year's sort of segmentation data. I've just created the model that finds brain tumors, and then
I see.
applying it to the task 2 data.
Okay, got it. But what I was thinking of, in which case, what I'm saying is, because there is, like, except for 8, and I'm just using the 8 as a placeholder, but I vaguely recall the number as 8, and I'll point to the notebook that Mehul pointed to in a minute after you're done sharing, because I think what you've done is very relevant. But so what I was thinking of is that except for those 8 images, in fact, we have the ground truth for the segmentation for all but 8 of our training images, even in task 2.
Yep.
Right, because of the overlap between task 1 and task 2. So it would, so from that standpoint, of course, if the segmenter is good, as you say, then it ought to give nearly, good results. But it would be even more precise because we have the actual ground truth for all but 8 images of the training set.
Yeah, so that was my plan really, was
so you could conceivably,
like, segmentation thing.
Yeah, go ahead.
Yeah, I was going to run my segmentation model on the task 1 data to see exactly how good it was at sort of identifying the tumors, and then use the task 1 data to improve the segmentation model. So it's as good as can be. But at the minute, I just wanted to get the sort of the segmentation model and the classification bit sort of working together, just to check I can actually
pipeline.
Sort of,
I mean, basically,
yeah,
build the pipeline
yep.
that then fine tune pieces of it. No, that's the better approach. But I was thinking,
yeah, sure,
that,
yeah, like by using the task 1 data, I can check it and improve upon it.
Right, or you can even think of it as task 1 data being like a fine tuning of the segmentation model.
Yep. Yeah, so like that's sort of where I was going to go next, but I've just had problems with Kaggle's data sets. They can be a bit temperamental. Yeah, because like I run these notebooks or whatever to create the NumPy arrays, but like then I try and create Kaggle data sets from those, so as I don't have to like recreate them on the fly when I'm doing training. And I've had like a lot of problems with Kaggle, just like saying, "Oh, I can't create your data set." It's like, yeah, half the time it doesn't even give like a reason. It just like says, "Oh, I can't validate your data set." So most of the week has been spent sort of like trying to upload, and like it takes a long time to upload to Kaggle for a data set as well. It takes about sort of 20 minutes, and then at the end of the 20 minutes, it comes back and says, "Oh, sorry, you can't create it," but it doesn't give you any reason for why not. So it's very frustrating at the minute.
Yeah, no, so I was having some other trouble similarly with Kaggle, so I don't know.
Yeah. Yeah. So I don't know what's the matter with it. It's just when I'm putting them up, it keeps coming back with all these rubbish messages or whatever. So, but yeah, like I've sort of like Googled to see why, and like people's like say, "Oh, Kaggle can just be temperamental." Like one day it can say, "We can create you like a data set," and then the next day it doesn't create the data set using exactly the same data. So hopefully next time I try it, it'll go okay. But yeah, so that's what I've been up to all week, is just remaking all the data and trying to get it ready. But as I say, the segmentation part's okay. So like hopefully if I can get like the task 2 data into a data set, then I can actually run the classifier as well. But I don't know what classifier to run yet, like, because you were like saying last week that EfficientNet 3D is not very reliable, so I need to.
Yeah, I actually I have editorial comment there too. I'm not now, after diving into the reasons why, there's another post that I read which leads me to believe that it might not be just the model. It might be the fact that, you know, the particular thing that that guy was doing might not be leading to the model learning at all, and that might be the problem. But I can't tell which it is, because at least the ResNet models I built from scratch seem to be better at this. So that's something that I would more want Mehul to weigh in, whether he has been able to get any better results or any viable results at all with this 3D efficient net model. Mehul, you there? Mehul, were you able
He's
to
on mute.
get any? Yeah.
He's disappeared.
Yeah, I think he's either not listening or he's still on mute and talking and we can't hear him. Mehul? Okay, seems like he's not. So let me just quickly share with you the couple of things I mentioned, so you can kind of. So can you folks see my screen?
Yes, Srinivas.
Hey, can you see my screen?
Yes, Srinivas.
Yep.
Okay. So, Steve, this is the notebook I was referring to. I think Mehul kind of pointed to this, and I can post it in Slack too. But this is one where this guy has shared his analysis of, the common thing I was saying, comparing patient IDs of task 1 and task 2 data. And if you see here, so this is the segmentation data set, and this is, I think, our classification, that is task 2 data set. So if you see here, he says that the extra elements, which means those in segmentation which are not in the classification, that's fairly high. And in the test set, there are 133 more elements that don't belong to the test set of the classification task. But that's, this we don't care about so much. This just helps us train a good segmentation model, right? But what is more relevant to us in the approach that you're taking is to see that there are 8 patients in our classification, that is in our task 2 dataset, which are in our class 2 training dataset, that are not there in the segmentation fine tuning or whatever that we may do. And for those, of course, you could always, like you're doing, just use the segmenter to predict for all of the items in our training dataset. But if you wanted to use ground truth data for our training dataset, you have it for all but 8. Does it make sense?
Yep.
Yeah, so I thought that was kind of helpful, relevant pointer to what's, but the key is getting a segmenter working like you have. I think that's most important thing. The other notebook or topic that I wanted to mention was this thing where, and I think your approach, Steve, is the best resolution for something that I had seen pointed out that find that notebook now, but that showed, the notebook that originally Mehul had pointed to, and it's a good notebook. I mean, it does set up the pipeline for at least the classification tasks and so on. But the because what this guy was pointing out was the classifier wasn't learning anything, which was the problem. But that was an important observation. Anyway, I can't seem to find that. What I wanted. Anyway, I don't want to keep the rest of you working while I search. If I find it, I'll post it to the Slack. But the important thing was regarding Steve, because you'd also brought up the question of, hey, I would, if I were you, I would say at this point, use both the efficient net 3D and also some other, I think, the relevant notebook that I was talking about. So let me share my screen again. Let me know if you folks can see my screen.
Yep.
Okay, so here is the thing that I was talking about, right? Like the thing he's pointing out is, you take the efficient net 3D with one MRI type, and the guy posted something and his score was like 0.6 something, and he's at a very high rank. But when you actually run it and you look at the training and the blah blah blah, the training loss and the validation loss, it really doesn't end up learning anything. And then the other interesting thing that in the discussion I saw, and he claims that it is, padding related, but I don't think it's padding related. As I said, I continue to be suspicious of the network itself. So Mehul, are you back? You're still on mute. I thought he unmuted for a minute there.
Yeah, sorry. Yeah, I'm back. Yeah.
Okay, so I was curious, were you able to get any better results or different results from the efficient net 3D? Did you do any submissions with that and stuff? Or
no, all my submissions have been like 0.5. Yeah, I was just going to say that when you brought this up. So what I did is I took that 64 by, I took that normalized voxel data set, right? And I figured out how to, I didn't use, the original notebook was reading dicoms and doing something. So I changed it to use the 64 by 64 and the 128 by 128. The training, in the training, the AUC, I think the highest I got was like 0.62. And it's hovering around there, 0.59 to 0.62, but every submission was just 0.5. And there are, yeah, maybe I agree with you. Maybe we can find another more. I saw other people also complain about the 0.5 issue. Like, when they make a test submission, they get 0.5. And somebody mentioned that because it's PyTorch, use like it's torch.eval, right? So they were making some description about that, like don't use torch.eval, use torch with no grad or something. But yeah, I haven't got a good submission. I made around like 10
Yeah, no, I
submissions.
looked at that and that doesn't make sense because I don't think that comment is valid. And then if you dig into the thread, then the guy finally says, oh, I'm just using this GitHub repository and I don't even know whether it's maintained. So which is the reason that I just feel
Yeah.
I'm not very trusting of the efficient net 3D model. But yeah, I agree. And then, so I switched to building a thing, but I've been building a 3D ResNet. But I have to submit on that and see how that works. I haven't made a submission using that yet. So, but and I also I'm not using the notebooks 3D DICOM as much as relying on the voxel data to process.
Maybe.
But an interesting site. Sorry, go ahead.
Yeah, I just one more thing. I also tried. So I normalized everything with that Bratz pipeline on my local machine. Right? So the entire 582 did all the Bratz pre-processing. So my images are 240 by 155. And because they are a template, right? So we know the template size. So the template is like, what I mean is the template is 240 by 240 by 155. But I can chop off like 40 slices on each side because in the template there's no brain there, right? So so I could get like a cropped 3D, but not with any segmentation method, just by knowing the template. So I had a 3D volume like that, and I forgot the exact size. So yeah, I cropped it, and then I feed that into Monai, and because it has a dense net, it has the family of efficient nets, but the results it doesn't. It's always sticking around 0.6, but maybe this 0.6 is better than the efficient net 0.6. You see my, but I haven't made a submission with like Monai processing and Monai. Yeah, Monai thing, and that's where I think I ran into one of the things Steve said earlier, or maybe this competition, or like maybe we should have like split it into a training kernel and a test, like have two kernels, like one for training and one for inference, because it's because when you submit it, you don't want to retrain, right? Yeah, so I have to make I want to make the Monai inference kernel, because if it works, there is a lot of it gives a lot of validated 3D models already created for like
I agree.
Yeah.
For classification, especially, otherwise you have to build it on the fly. That's what but I mean, I was able to build one on the fly and
Yeah.
for different REST nets, but not dense nets, and because then each of them you'd have to build.
Yeah, no, this one is, I'll share some code. The thing I really didn't, the reason I don't want to give up on Mona is like I could build a custom dense net with like 6 lines of code. And it's really nice that way, that it just lets you. So I'll share it in the Slack, and then custom dense net. And yeah, I couldn't get the REST nets to work for some reason, but I could get the dense net and efficient net to work, but I haven't made a submission with those two yet. Yeah, that's it.
Yeah, and if you look at, there's one other tidbit that I thought was, something interesting that didn't strike me, and I thought that was a useful kind of observation. So I just wanted to share that, which is referred to in the comments to this kernel, right? So I think I just thought this was interesting that if you just submit using that, which we are not doing because as we said, as Mehul just said, and I've also done, I mean, we're not using the 3D DICOM data, you're kind of using the voxels, and Steve obviously is using what I would consider the perfect approach. But what I thought was interesting aside that is useful, get to it. What I had somewhere in this, but anyway, if it's not in the comment, I saw it somewhere that bottom line, if you just do negative log of 0.5, it is 0.69 or 6 something. So that was something that somebody pointed out, and I thought that was an interesting stuff, that if you just guess 0.5 for everything, then you're, the stuff that you get is around 0.6 something. So if you're stuck in your loss with about 0.6, something that basically says most of your output is just hovering around 0.5. As we saw with the efficient net 3D that Steve shared, I think a week or so back. I thought it was in the comments to this, but maybe it's not. Maybe I saw it somewhere else. But I thought that observation was an insightful one too. That
Yeah,
if you
I think that's what I've seen before. It's like, yeah, so if your model doesn't actually sort of commit to saying if it's a 1 or a 0 and just sticks everything out about 0.5, then you get like a reasonably good leaderboard score of whatever that kernel was getting, like 0.68 or whatever it is, or 0.64 or whatever. So I think if you're not getting a score above 0.64, then your model's not actually really learning anything. And I think, yeah, like the values you showed last week as well, at least the classifier that you were running did appear to be going towards 1 or towards 0, as opposed to, yeah, like the results I was getting, even though it trained for hours and hours, it was all sort of 0.52 and 0.48. It was all just hovering about 0.5 for its prediction. So it wasn't really committing to anything, but yeah, getting a reasonably good score.
Yeah, that's why Mehul's point, Monai or the RESTnet that I built on the fly, I trust them more than the efficient net 3D stuff that the guy was using, and I've seen a lot of people using, because it just seems to do what you're saying, Steve, hover around the 0.5 and thereby get just the 0.6 something value, but not really give or get variation in the scores.
Yeah, I saw like on the Monai page they've got, is it DenseNet 3D or something they've got?
Yeah, that's the one. Yeah.
Have you used it, Mehul?
Yeah. I'll give me 2 minutes. Yeah, I used DenseNet. So they have a DenseNet 121, a DenseNet 169, DenseNet I think 2.1 something. So I used somebody's working on something in my backyard. um, yeah, this had also. I used DenseNet 169 guide. It worked out of the box. I didn't have to make. You just tell it that you have two, like two output classes, and then like four. I tried. I could fit all four channels. Yeah, that was one amazing thing. It was. The images are quite big, like definitely bigger than 64 cube, and I could feed all four channels. I need to check my batch size.
When you say four, what is your four channels?
So,
just a duplication or?
No, the flare, T1 weighted contrast, or all the four exams.
Okay. So you're using it. That's what I was beginning to want to try to do. But so the input is nifty, I guess, right? Though.
Yeah, I did nifty, but I can. I saw they made it pretty flexible because they use PyTorch dataset and data loaders. I haven't.
Because the issue that I saw is wouldn't you have to either convert all the images to Nifty, store them, but then you also would need to figure out how much time it would take to convert our test thing to not just the test, all of the tests, right? The public and private to Nifty on the fly if you were to apply Monai, correct?
That's right. Yeah. And that's, I need to check that. I saw there was some newer kernels. So there is another Python based library called Torch.io, and somebody shared a notebook with. I think he's the maintainer of that repository, so he wants to show like how easy it is to use his library. So he was doing all the pre-processing with his with this Torch.io.
Yeah, I saw the Torch.io notebook you posted, but that didn't convert to Nifty though. That just made the processing simpler within PyTorch, but I didn't see it go to Nifty because the limitation of using Monai, which is kind of frustrating because otherwise it would be really cool, is that you have to go to Nifty, right? Which means all our data has to be converted on the fly.
Let me try and find one thing for this next. Let me try and find out if we can input NumPy files to Monai instead of Nifty. I know that people were inputting like JPEGs to it. Because that was from a previous from the CT Kaggle competition. Somebody figured out, okay, I convert these to JPEGs or PNGs, and they figured out how to input that to Monai. But I think it should be possible to input NumPy. We want to input NumPy arrays, right? So is that the or even
because we've shown that building the voxel, right, like the guy did, you can and the voxels are basically NumPy arrays, right? And so at least doing that can be done very simply, and you ran it, I ran it, Steve ran it. I mean, on the test data, so all that conversion can happen very quickly within the time bounds we are provided, right? Whereas the problem I thought we were having with Monai is if it's Nifty requirement, the converting to Nifty of all of the tests is going to limit us, and that's too long. If I recall correctly, I could be wrong, but I thought that's a limitation why, while that approach can give us results, we can't really use it eventually because you run out of time limits, right, if we have to go to Nifty.
No, Srinivas, just one clarification. So there was there is the Monai which will do all like the classification on the Nifty. So previously I shared, I was using that CAPT Bratz pipeline, right, which is like these Unix
Right.
binaries to do all the pre-processing, registration, blah blah. So that it's the Nifty conversion itself is fast. It was the registration that was too slow. So
Oh, I see. So you're
yeah.
saying we could still use Monai without and yeah, because we were anyway saying registration may not give us anything additional. So unless
Yeah.
unless you're doing it the way you are, which is with 4 channels and each type being a channel, because in that case you will have to register and align.
Right. Yeah.
Right? Because in that case, as I discussed, I think you were in there when I mentioned in the case that you are using every layer as a every layer of the channels or every channel of the 4 channels as a type, then you would need the registration because you don't want, and now I'm switching analogies, you don't want a red bear and a blue bear and a green bear to not be in the same locations if you're looking at a bear in an RGB 3-channel image, right? So it's that kind of analogy when you're trying to put every MRI type as a channel. But if you don't do that and you just use a single channel and use a single type as a single channel, then the registration isn't necessary. And if that is the case, and if you're saying that it's not the conversion to Nifty, then it may not be a problem. And just like converting to NumPy, you just convert to Nifty and use the Monai built-in model to do it. Okay.
Yeah, I was just trying to see if I can share my screen. The page I want to, okay, it's not coming up. While it comes up, I just, Steve, the segmentation you did, I saw the last year's competition, like they were, so I was trying to read up a little bit, but so the tumor has like 4 parts. Okay, so there is the brain tumor, and then there is like bleeding, or not bleeding, like water accumulated around the tumor. I think they call it edema, but it's just like water accumulating. So there is a primary core. Oh yeah, the inner core is like dead tissue, so it's called like in necrosis. I don't know. They just have these fancy terms. They're just learning the right. So
Yeah.
So the
I
innermost.
saw that too. But I was.
Yeah.
Go ahead.
Yeah. So the 4 things, so the tumor can be segmented into 4 things, into 4 components. And so I was thinking maybe like the water doesn't contribute much because it's just like there's some accumulation around it. So if we can focus, but I think from your segmentation image you were showing right now, you only have one segmentation output, right? You don't segment into four classes.
As you say, like in the Bratz 2020 data, the segmentation masks that they give you do have the 4 classes, and like originally I was doing that, but then I've just changed now to make it binary. So like basically anywhere they've got like a segmentation value, I put that to 1 now. So like I get like the biggest area. Yeah, because basically I just wanted to sort of be able to cut down the full brain scans into just the region where the tumor is, but yeah, I didn't want to sort of throw away any of that. So
yeah, that makes sense. Okay. Yeah.
But as you say, like
yeah,
perhaps
that makes more sense
regions,
to Mehul for me.
Okay.
Yeah, so I wasn't worried about the different types of tumor or whatever. I was just worried about where it was.
Mm-hmm.
And while I also exactly had the same thought as you, Mehul, that maybe we could use like the thing, but meaning the necrosis piece. But for that, the missing domain knowledge we would need to have is which of the four is likely to contain the
Right, yeah.
MGMT marker,
Yeah.
right? And
Yeah.
in the absence of knowing that, I would rather go with the Steve approach, which is what I decided is the better approach to go. Because why? I mean, limit, unless you know that in the effusion, or I think they call it effusion or whatever, edema or something, why exclude that if we don't know that that MGMT marker might be in that too, for all we know?
Right.
If we know that it is in one of the four and it gives the four, and the other problem with that kind of an approach is, I don't know whether, I thought I looked at 2021. I don't know whether even in 2021 they have the same four available or not. So if that is indeed the case, then I think Steve's approach is probably the best. Take all of the pixels you can get, identifying as any part of the tumor, and then go from there, because you're significantly reducing all the other pixels anyway. So you don't really care whether you're throwing in a few hundred or a few thousand pixels more compared to, like millions of pixels that don't matter.
Yeah. Okay.
So I think Steve is by far the best along this stuff right now. So hopefully, and the one thing I would say, Steve, in all the discussions I've seen, is totally build kind of maybe a 5-fold validation and just rely on that. Don't even look at the public leaderboard. I think you yourself were saying that earlier, but it just, the more I look at it, the more the 87 examples are never going to give us what are close to what could be the answer for the others.
Yeah.
Cool. I think, Mehul, yeah, if what you're saying is true, and if you can share the Monai links and stuff, or even show us if you're able to bring it up, that would be cool, because as you say, Monai has the built-in models. We can try multiple of them, and much like Steve is doing, but a crude approach could be just, even like you said, just use particular slices and see whether the score improves using that, which are all good indication that at least the methodology is working. And then once the segmenter is done, so were you using, Steve, something, a result of a Bratz 2020 competition segmenter?
It was one that was like developed for that competition, yeah. So it's a bit strange actually, because it's I think there's how many? I don't know. Say there's like 300 like different studies or whatever. It only uses a very limited set. It only uses like about 20 of them to train its model, but it seems to do pretty well just from like training on like a subset total set.
It's pretty amazing. From 20 samples.
Yeah, so like it takes 20 samples, but it is like it's doing like 2D unit segmentation or whatever. So it's like on each slice out of that. So it ends up, 20 samples. It has what 4,000 2D inputs or whatever. So yeah, like I'm just running on that at the minute.
Amazing.
Okay, let me try and share my screen. Pop up. What is this?
can see it now.
Okay. Yeah. So there are two sets of tutorials. I found this one better, because they had a boot camp last year, in 2020, and I learned, yeah, the two new things. One is like, uh, with I'll just quickly walk through it. So yeah, these are some of the transforms that are already uploaded, that are available for data augmentation. Um, yeah, this is just something to read the Nifty files. One sec. Yeah, they talk about the splitting the data. Then you just make a small class. That's it. And I was like, and then you just have you create your data set, and then you're using the Torch, PyTorch data loaders. So I think I just need to. So for example, I think I just need to create a class so that we don't, just use NumPy as input to it. And then Steve, this was the DenseNet model. So that's all you do here. You just say, um, in um, in this case, they are working with 2D images, so spatial dimension is 2. But yeah, I have the node. Yeah, the machine I normally work on. Shoot, it's so silly. They changed our office, and then the network is terrible. So it keeps losing internet connection. I had to shift away from that machine. It's like, okay, it's 2021. We don't have a good internet connection. Yeah, it's just, anyway, so I'll just show. But basically, what I did for the 3D is, so spatial dimensions is 3 in channels. If you use only flare, it's 1. But if you use like 2, 3, 4, so you can. So I think I ran all those experiments. I ran like with only 1, only 2, only 3. Yeah, and then out channels is the number of classes. So that's it, and this is the standard PyTorch 2 device.
Are you using out channels as 1 or 2?
2. Yeah. Out channels as 2, right? Yeah. And then
Is that a pre-trained model?
yeah, that's a great question. They have an option for pre-trained equal, so you can say pre-trained equal to true or false. And let me do one thing. Let me see if I can do they. Oh, they don't. I thought they could open this in Colab. Give me 1 second. Then I can just show you. Yeah, tutorials, 3D classification. So that's the one I started with. Yeah, this one. Yeah, okay, good. What? The link doesn't work. Yes. Why is it asking me all this? What? Yeah, I wanted to just show you. Okay. Yeah, okay. Import. I just need the Mona import right now. Yeah, anyway. Okay, I got the Mona imports, and the model is. Give me 1 sec. Yeah, this is the yeah, 3D example, where, I was using this one, and the pre-trained stuff. Oh, sorry, what did I forget? I forgot something. It did have an option for pre-train. I just couldn't see. Okay, yeah, now I have Monai. Yeah, here we go. So blah blah blah. Yeah, pre-train. So you can say, yeah, you can say true or false. I couldn't figure out what I was trying to see is what they pre-trained on. And so this is created from another class called yeah, just this one.
In that, it has the comment that pre-trained only worked on, was that your comment? Only worked on 2D.
Oh, wait, let me go this one.
You look at the code, look at the bottom.
Oh.
If pre-trained, it only works on spatial dim is 2.
Shoot, I don't see that.
No, on the right, where you
On
have
the right.
opened up the code. Look at the bottom.
Oh,
of
this no, this is no, this is not mine. This is just there when this is written in the oh, interesting. I didn't see that.
So that means they pre-trained on 2-channel or 2D, right?
Right, they pre-trained on 2D probably. Yeah. Okay. DenseNet 121 pre-trained. Oh yeah, okay, with optional pre-trained support when spatial DAM. Yeah, you're right. It's only for, yeah, that's in there. Oh, I'm just blind. And what about the regular DenseNet? Is it the same? I guess same problem then. Spatial. DenseNet, blah, blah, blah. Wait, that's the rest. See, here they don't talk about, it's silly. Why don't they talk about the this all these terms are just for exactly following the original DenseNet paper, so it's very easy to match. Like this is basically there are 4 dense blocks with and if you open the paper, it will match exactly after that. DenseNet. Steve, I didn't see the DenseNet 3D. I just know this one. I just see DenseNet and I see it should tell me all the options. Yeah, these here. Yeah, that's the one I remember. DenseNet 121, 169, 201, and 264.
Is the spatial dims parameter, is that whether it's 2D or 3D?
Yeah, exactly. Yes. Yep.
And so, yeah, like if you choose 3D, then it looks as if you can't have a pre-trained 3D.
Yeah. Yeah. So then, right. Yeah.
So in the notebook you're looking at, is that their example of 3D?
Yes. Yes. So they have Okay, so they have this is basically just 3D, and they here the task is they're just trying to say like if you can say from the MR if it's like a male or a female. This notebook was quite good because they also share like some of the nifty data, so you don't have to waste time preparing them. So I was just learning how to how to run their stuff from this. They talk about like I can just quickly, so you can basically have your transforms, right? So but they have like at least 100 different transforms. It's crazy. It just they've already implemented all of that. And I'll show you that. So you define your transforms. You have your image data set, and then so the transforms goes with the image data set, and then data loader is just it's PyTorch, right? It's pure PyTorch, and that's it. You basically make a train loader and a validation loader, and so
yeah, see there on their dense net, they've got spatial dims equals 3. So.
Right, exactly.
Yep.
Yeah. And they write only one, so they only have a T1 weighted. So I can't show you my notebook. So in my notebook, I was playing with this number of in channels was like 1, 2, 3, 4, and then this is I think this, I don't remember seeing this in Keras and TensorFlow, but maybe you guys have. So what they're saying is this is a typical PyTorch training loop, right? Where you are writing all this boilerplate code, right? For example, you have to say loss.backward, you have to say optimizer.step, and why did you have to do 0? Yeah, before every, this was, as you loop through your batches, for every batch, you have to set the gradients to 0. Though one person said like, in the plain vanilla version, in every batch you set the gradients to 0, but you could do something more intelligent than just so that's that. And then that's doing the backward propagation, I want to say. And when you are in your so that's for the training training the batches, right? And then in the validation, you have to say torch.nograd and blah, 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 and then just whatever.
Yeah, this is all just standard PyTorch.
Standard stuff, right? Yeah, and so they kept talking about like Ignite, so you don't have to write all that.
I think those are all variations headed towards something like FastAI, Ignite, Lightning. But it's all just abstraction. And if you use FastAI, then you're just basically on the one end of that abstraction, and all these steps that PyTorch guys have, some guys have written up on PyTorch is just heading towards what you eventually get with something like FastAI Mail. It's just that they're all baby steps towards that. That's all. You just keep abstracting away stuff that you need.
Right. Here they had something more about okay, I see, that's it. And the last thing was, I think, I thought this was quite nice. I was looking at and then just so these wait, did they do? Yeah, so some things like center spatial crop is available. So that's what I was. I knew that in my. Do I have that image open? File close. think when I display it, it doesn't like it. And I'm sharing. Okay, open a new window. Why does it look like this? Yeah, so because everything is registered to template, right? So I can just do a crop like in the center. So I said like, pick from slice 20 to something 120. Yeah. And then same on these axes. But we don't have to do that like the other method Steve had. That works well, because they have done a good job with the cleanup, so it's very easy to know when to crop, right? And then of course the segmentation also will do better job. Um, and then these were the cropping transforms, all the different types of croppings or paddings, and then these are the intensity transforms. So like I saw some new stuff here, so I knew like adding doing Gaussian smoothing and stuff, but and adjusting contrast, but they also had like Gibbs noise was new to me.
Do you know if some of these transforms are specific to sort of medical imaging?
Yeah.
Or would these be just the same as you would get like in albumentations?
I want to say like the Gibbs noise is medical imaging specific. The random Gibbs noise, and there is like this affine and elastic transform. So these might be. So the elastic transforms might be are medical specific, maybe. No, though it's non-linear. It could be no, maybe even I haven't checked if albumations did that. So instead of basically the idea is instead of just rotating or translating in 3D, you do more sophisticated transforms. Like wait, I have to show you an image to show you what that elastic transform does. Maybe. This is like a doing the Brat segmentation. I'll try and run like this model on the Brat's data, and then we can compare how well the model you have does with this model. Like, I think I just had to prepare the Nifty as input.
Yeah, cool.
Yeah. Wanted to show where's the transforms. Okay. Yeah, this one.
I noticed that other library you were talking about as well. Was it
Torch.io?
Yeah. Yeah, like it's got like a full set of its own transforms as well.
Yeah. So yeah, I'll go to the. So see, this is the regular, and then this. So the random elastic, you see, you can get these little waves, and like these little things around in. So these local deformations are very hard to get without, like, if you use just translations and rotations, you can't get this. It's almost like you had a bed sheet, right? And you can crumple some parts of the bed sheet, right? Like just make like deform, do local deformations. So that's what's possible with this random. But then there are too many parameters, right? Just like just see that you can do this. You can, yeah. It would be like elastic deformations. Like maybe 10, 12 years ago was like somebody's PhD thesis. There's so many parameters and to do this, and then maybe Torch.io has better examples. Yeah, this is This is the guy. Ah, okay, cool. Yeah, there he's done. Yeah, random noise. Yeah, it's not so easy to. Yes, you see here, like in the affine. So the affine is only translation, rotation, and shearing. So you can shear in X, Y, or Z axis. But here you can do much more with. If you see here and here, you'll see some nice differences. Ghosting, okay. Yeah, that's some very medical specific, like a ghosting artifact. It's like, remember when we have the Fourier transform, you have the Gibbs phenomenon? I think it comes from that. Like this one also might be medical specific, like a spike in the image.
Yeah, actually, like when I convert my DICOM images into NumPy, I end up with sort of funny banding effects on them sometimes. So yeah, like these transforms might be quite good because they sort of replicate that.
Yeah, he's got a nice collection. Yeah, and it's pretty big community, like contributing to it. This guy, and I see. I remember this one was the original one, but now nobody's using. Okay, so I'm maintaining. Yeah, the last thing about Monai was they because it's from NVIDIA, right? They are they had in version 0.6 was the latest one, and they said something. I know, like that automatic mix precision is like you don't have to do anything special to get automatic mix precision when you use Monai. But there was also like a faster way to load data sets. So they okay, I was trying to understand that, but I didn't understand it yet. So they talk about caching the data sets to get more speed, and like this notebook is only about data set loading and yeah, data set caching. But maybe yeah, they say, yeah, they talk about blah blah allowance for persistent data set, something. And this zip, yeah. So the, okay, that's it. Let me see. This week I'll try to figure out if you can do NumPy or even do the nifties on Kaggle on the test set. So if that, I think on the inference we have 9 hours of compute time, right? I think we checked that last time. So if the nifty conversion can finish in 1 hour, we should have plenty of time for.
When I'm converting my images now, I'm using there's a thing called Empire. It's like a what is it, parallel processing thing or whatever. So I can like greatly speed up all my conversions.
What's it called again?
MPIRE. Yeah, if you just put Python or whatever in that.
Ah, cool. Okay.
Yeah, multi-processing library. Yeah, so it's really easy to use and speeds it up a lot. Yeah, so I can like sort of process 10 images at once effectively.
Oh, nice.
Yep.
Yeah. Okay.
I'm actually going to have to drop off here because
yeah, me too.
Out, so.
Yeah.
Okay, thanks, guys. I'll see you all next week. Hopefully, we'll have made progress along.
Yeah.
Dimensions.
Okay, cool. Yeah, like
see
the Monai thing looks good, so I'll hopefully get that.
Yep.
Cheers. See you next week. Bye.
Thanks. Bye.